Hello guys! In this video we will write in order of the binary tree again, but today we will do this in a different manner. We will write a function which takes on input a tree and a node in the tree and produce an index of this node in the order of this tree. So you can say that you can just take classical in-order algorithm and build a list from the tree with it and find the element in this list, and this index will be this value to this function. But we will do this in a different manner. Okay, how we will do this? Okay, first of all we will start from writing a simple helper functions. In a previous video we write this function which called path, which allow us to build a path from a node to some node with extra information which contains the direction from each node where we go, to the left or to the right, to the next node, and so on until the end. If you want to understand how we write this function, how it works, look at the previous video. I will put a link in description and you can see it below. But this is a simple function which built a path from a root to a requested node A, and also it produces a direction, so it returns a list of tuples. And we need to start from writing some helper function. The first helper function, I will call it count, and all it do is just count the numbers of nodes in the tree. So if we have an empty tree, of course the number of nodes is 0. Okay, I will show you a definition of the tree data type. What we used, it's either empty tree or a node with some value a and two binary trees, left and right. So if in the empty case we return the 0. So if we have some node with value a and nodes and subtrees L and R, in this case we already have one node and we have count L nodes plus count R nodes. So this function is it's a very simple function. Let's save and let's check this. So we have this tree, I built it in the tr variable. Not variable, I think this is a function. Yes, in Haskell there is no variables, so it's just function that returns me a tree. So I will just reload this module and count the numbers in this tree, and we can see that it works as expected. We have seven elements in this tree. So the next thing I want to write is a get subtree function. What it means, get subtree, it takes some node in the tree and this function returns me a subtree which goes from this node. So I can take any branch of the tree using its node, or the root of the branch. So what's the type signature? We have some A and battery of A, and we will produce a battery of A, and of course we will produce a maybe battery of A, because if there is no node, there is no tree. Sorry. And also we need to constrain our A type with a Q instance, and I think that's all for type signature of this function. And let's define this function. If we have some empty tree, no matter what the node they search, where is an no this tree, no such a tree. In this way they return nothing. Okay. And if they have define get subtree for some node A, for subtree for some node A, and we have a node which contain A, left and right subtrees, and also at this step I need to name all this node with some name, because if this node contain A, I need to return this node. So, and let's just check this case. If n is equal to our searching 0, then when the return just t. Okay, and otherwise, if it's not equal to this A, then they need either search in the left subtree and they need to search in the left subtree and in the right subtree, and one of these will contain our, if it present there, of course, will be contain our subtree. So, and we go to recursion here. I think we call get subtree with our A, and with L. Okay, this will be one possible result, but there is another possible result if it's in the right subtree. So, and how to combine these two things? These two things are maybe value and maybe is alternative, so we can use this operation to combine these two things, and this get us, if we have one, if they have one of these values will be just, this function will return us this just value. So I think that should work. And I need to import the alternative, and this module call its name, I think, import control applicative. I think it's defined there. Okay, let's try to reload our module. We have some problems. Of course, let's rename this to n and this to n and this to n, because I already used this a here. So reload, it's done, and we try to get subtree from our tr and with the node b. Yes, we take this subtree, and if I call d, for example, yes, it works as expected. So now we can get our subtrees for any node and count the node of any tree. We have these two functions. Okay, and next thing we need to do is, okay, let's look at this image of Inorder. Look at this image of inordering. So how Inorder works? How can I just take some node and count its number in an order, its position? Okay, if you look at, for example, if we want to find index for 3, okay, look at this path to the root, from 3 to the root. So if we go up, we can build this path, and we can build it with the extra information of rows. So for 5 we have go to left, for 2 we have go to right, for 4 we have go to left, and for 3 we have the end. And so how this 3 is determined by this path, and it's determined by this path. It has all the information to calculate this number. So if you look carefully in this picture, you can see that to count this number, we need to take first of all the left branch of this 3. In this case it's empty, but we need to count all the elements of the left branch of the 3. And then we go, if we go to the next node of the path, we count this left path because all the elements from the left side of the tree will be before this node in an order, and we must count them. And also I want to count these left sides and left sides from all the path up to root. If I count and sum them all, I will get the number. This is the main idea. So here we have no left tree and nothing to count. We have these 4. From these 4 we go into the left. This means that these 4 in order will be from the right of this 3 node, and they didn't need to count this. We doesn't count this because it doesn't take space from the left, and this just skip this because it goes from the left. We have this extra information about routing. But if we have, and then we go to the 2, and from 2 we go to the right, And this means that in order the 2 will be taken some space from the left, and we need to count these 2 and all the left subtree of these 2. And again we go to the 5. From 5 we go to the left. This means that this doesn't take any left space from 3, and we just skip this. So we skip all the nodes from which we go to the left, and we count all the nodes from which we go to the right, and also we count the left the total number of nodes in the left subtree of such nodes from which we go to the right. Okay, I think you got the idea, and let's go to our code and clarify this. So let's define this function. So this function, I call it Inorder. I will call it IC, and it takes some tree, and it takes some start node. Start node. Doesn't good name, I think. Search node. And how can we start to write this? How can we define this program? So I want this function return as an index of the node, and to count this index we need to count all the paths from which we go, all the nodes in the path to the root from which we go to the right, and all them left subtrees count. I talked about this in the previous picture. So this function should return some number first of all. Okay, we need to start from our path function, which find a path from our start node in our tree to the root. Okay, then we have this path. We have this. The next thing, what we do, we can see that our path function has a maybe value which contain a list. So I need to extract this list from just function, and then I extract this list. Okay, let's run our function with some node, for example b, and our tree. Okay, we've got this thing. You can see that any of these tuples will give us some number, and in the end they need to summarize these numbers. What I mean, it give us some number. Remember this picture. Then we go from there. Then we go to the right. Then the node. Then the node reserves some space from the left. So we need to count this. Okay, let's just fmap this list with some function. I will call it C. I will call this function C. And of course I need to define this function. How can I define it? I will define it like so. So this function will take some pair with a node name and its direction. I'll call it D. And I pattern match it, and next thing I do is start to look at this direction, case D of, and this, if this direction is to the right, this means that we need to this node reserves some space from the left, and we need to count this. And how can we count? First of all, it's reserves some space by itself. So this means that we have already one. We have already one, and also we need to calculate a left subtree. Count the nodes in the left subtree. So first of all, we need to get this subtree, okay, with our get subtree function, and node n for get subtree for node n, and for our tr, I think, yes. Okay, we get this subtree. The next thing, we need to get the left subtree of this tree and calculate its count, number of nodes in this left subtree. So, and for this simple task I need to write a simple helper function, which I will call a left count. It will take some tree and count the number of the left subtree, not a total tree nodes, number of left subtree nodes of this tree. And if the tree is efficient, of course there is a zero such nodes, and if the tree is some node with no matter what in the node and left subtree, and no matter what is the right subtree, in this case we need to count the left subtree. And I think that's all. Okay, and now we have this subtree. They need to, it is in the mapping, so we need to access the left subtree to fmap this mapping with our left count function. Yes, we will return. Now in this expression we have maybe our left subtree, nodes, number of nodes, so it's maybe number, and we need to increase this number by the 1, because we also count the n node itself. So the next case, if we go from the left, this means that we need to just, this node, if you go from the left, this means that this node will be from the right, and it not take space from the left, and we didn't need to count it. So we return just 0 in this case. And if this node is end node, then what we do exactly what we do when we go from the right. We count this node itself and we count all the left subtree of this node in the ending position. And now what will this expression give us? We will here we will get a list of just of numbers, and we need to remove these justs from the list. So what I mean, let's try to compile this function. I talk too much and I don't show anything. Okay, case. Oh, sorry. a little bit, make a little bit noise with the case. So like so, not in scope, left count, try so, what I forgot, I don't see. Okay, it's loads. So let's try to run this. Our Inorder count with our tree, and for example for node A I got just 4. You can see that it has a list of just 4, and I need to remove this just from the list. And for such a thing there is a nice function, and it's called cut maybes. Let's look at its type signature. Cut maybes. It's take a list of maybes and produce a list of A's. So it remove all nothings. It's just filter on nothings, remove them, and take the just and remove the just constructor, and produce a new list of A, which contains inside these justs. So we calculate this, and we get this list. And the next thing, what do you think we need to do? Of course, we need to summarize all these things. And this, if we summarize all these things, let's try to reload, and magic happens. We get the number. All this order. So, what this mean? This means that I now can get the number of any node, for example B. For example, for node B I can this number, okay, and I think that it's correct. And for node D I can take this number, and it's correct. Actually, I can get it for any node. So if I construct the list of all my nodes in this tree, how can I construct a list of all these nodes? I just do this by the hand. I have A, B, C, D, E, F, G. A, B, C, D, E, F, G. But I think I can do this with any of Inorder, pre-order, or level order, traversal, or Inorder traversal itself. Classical algorithm. Okay. So if I get this tree, now I can I can write so why I can let's take this tree or this list, and for each of these nodes I want to find its number. So I will fmap this function, and I need the lambda here, which will get a node, a searchable node, and then we get the searchable node. It can use our IC function with our tree and with this node to give me its index. So, and I can take this index and build a pair with this node, build a tuple with this index and this node, and so I will get a list of tuples which contain node and its index. So let's run. I need to reload, of course. Bams, you can see that we get this, and actually I can define it as a function like so, I think, which takes some tree and produce a new function. Okay, it will take some tree and list, and I can call it Inorder tree and level. Bams. And you can see this is in order. So I need to check it with my nodes. Okay, A have 4. Look at this tree. That tree. A have 4. B have 2. C have 6. D have 1. E have 3. F have 5, and G have 7. Yes, it works as expected. So I think that's all. Of course, this is not optimized solution. For Inorder tree classic algorithm is much faster, but it allows us to look at some other angle to this problem and to see how our indexes of Inorder are depends from the count of all the nodes in our path to the root and its left subtrees. So it's some kind of dependency, some kind of function from this structure and left some branches to this number, some kind of mapping, and they implement it using Haskell. So guys, thanks for watching. Push like button, push subscribe button, write comments, and see you in the next video. Bye.